White blood cells are also known as leukocytes. White blood cells can be distinguished from red blood cells by their larger size and by the presence of a nucleus and other organelles. White blood cells help defend the body against an invasion by pathogens, and they remove toxins, waste, and abnormal or damaged cells. There are two groups of white blood cells, granulocytes and agranulocytes. Neutrophils, eosinophils, basophils, and monocytes respond to any type of threat, and they are part of the nonspecific immune response. Lymphocytes respond to specific individual pathogens, and they're responsible for specific immune responses. Now, unlike red blood cells, white blood cells circulate for only a short portion of their lifespan. They migrate through loose and dense connective tissue of the body, using the bloodstream to travel from one organ to another, and for rapid transportation to areas of invasion or areas of injury. Circulating white blood cells have 4 characteristics. All circulating white blood cells are capable of an amoeboid type movement, meaning that they can wiggle their way through capillaries and squeeze in and out of small spaces through the tissues. All white blood cells can migrate outside the bloodstream through a process called diapedesis, and you can see the PED portion of that word, which is in reference to foot. So they make these foot-like extensions to wiggle out through portions of the bloodstream. All circulating white blood cells are attracted to specific chemical stimuli, which is referred to as positive chemotaxis, and it guides them to pathogens. Neutrophils, eosinophils, and monocytes also have the capacity to engulf damaged blood cells, toxins, or other foreign material in a process called phagocytosis, which is very similar to the process of endocytosis, which I've described for you before. Let's start by looking more closely at each of the different white blood cells, beginning with the neutrophils. Neutrophils are probably the most populous, making about 50 to 70% of the circulating white blood cells. Neutrophils have a very unique shaped nucleus in that it's multilobular and somewhat globular, dense and contorted. Neutrophils are usually the first white blood cells to arrive at the site of an injury due to their ability to perform positive chemotaxis. Once they are at a site of injury, neutrophils are able to attack and digest bacteria by the process of phagocytosis. Literally, they're big eaters. They engulf that bacteria. You'll see an increase in neutrophil percentages during bacterial infections, and this is one of the reasons we perform a white blood cell differential. You'll see that shift in the percentage. Another granulocyte is the eosinophils. Eosinophils are relatively rare, making up only 2 to 4% of the circulating white blood cell population. Eosinophils are about the same size as neutrophils, about 2 to 3 times the size of a red blood cell. However, eosinophils have a deep red granules and often they only have a 2-lobe nucleus, looking very much like a horseshoe shape. Eosinophils are phagocytic, but they typically attack through exocytosis instead of phagocytosis. And they do this by releasing the toxin components of their granules. So you'll see an increase in eosinophil populations during parasitic infections or during allergic reactions. The other granulocyte is the basophils, and these are somewhat smaller than neutrophils, although very similar in size. Basophils are relatively rare, making up only about 1%, sometimes less than that, of the circulating white blood cell population. The dark purple to black staining granules typically contain an anticoagulant called heparin. They can also contain an inflammatory compound, which is called histamine. One of the agranulocytes, the monocytes, is about twice the size of a red blood cell, sometimes even larger if they're activated. Monocytes have a very large kidney bean-shaped nucleus. They usually make up between 2 to 8% of the circulating white blood cells. Monocytes typically will migrate into tissues after circulating through the blood system, where they become residents and can become macrophages. Macro meaning large and phage meaning eater. These are very aggressive phagocytes. They do a lot of the cleanup of damaged blood cells and other tissue cells. They clean up garbage and excessive debris. If they encounter any foreign material, they will phagocytize that as well. Last, the lymphocytes are another agranulocyte white blood cell. They're only slightly larger than a typical red blood cell, and their nucleus takes up almost the entire cell. After the neutrophils, they are the next most populous at 20 to 40% of the circulating white blood cells. And there's a large number of lymphocytes that migrate in and out of the tissues and the lymphatic system. Some of these lymphocytes can attack foreign cells. Others will secrete antibodies into circulation. There's two main populations of lymphocytes, the T lymphocytes and the B lymphocytes. And we'll discuss those two different populations and their roles in the lymphatics chapter more. Now, as I mentioned earlier, the red blood cells are not the only population of blood cells to arise from hemocytoblasts. Hemocytoblasts produce lymphoid stem cells, which give rise to lymphocytes. They also have myeloid stem cells, which give rise to the other types of formed elements. Various hormones are involved in the regulation of white blood cells. White blood cells other than lymphocytes are regulated by colony-stimulating factors. Prior to an individual's maturity, the thymus hormone, thymosins, are going to regulate the T lymphocyte maturity. And after maturity, lymphocytes development is stimulated by exposure to antigens, such as foreign proteins, cells, and toxins. Hemocytoblasts at the top produce the lymphoid stem cells, which migrate from red bone marrow to peripheral lymphatic tissues like the thymus, spleen, and lymph nodes. The process of lymphocyte development is called lymphopoiesis. And as is the case with red blood cells, hemocytoblasts also give rise to myeloid stem cells. Basophils, eosinophils, and neutrophils complete their development in the bone marrow. Monocytes begin differentiation in the red bone marrow, and then they enter the bloodstream. They complete their development when they become free macrophages in peripheral tissues. The last component of formed elements are the platelets. Notice how the myeloid cells can also differentiate into a megakaryocyte. These megakaryocytes continuously shed cytoplasm in small membrane enclosed packets, which later become platelets. These platelets initiate the clotting process and help close injured blood vessels. Blood contains 150,000 to 500,000 platelets per microliter. About a third of the platelets in the body are in the spleen and the other blood-rich organs, acting as reserves for a blood clotting emergency. So platelets play a very important role in homeostasis, which is the process, not homeostasis, hemostasis. So hemostasis is the process that halts bleeding and prevents the loss of blood through the walls of damaged vessels. At the same time, it also establishes a framework for tissue repairs. So before we start talking about hemostasis's 3 overlapping phases, recall from the tissues chapter that blood vessels contain smooth muscle and an inner lining of simple squamous epithelium. A cut into the smooth muscle leads to a vascular spasm of the smooth muscle. This is going to shrink the diameter of the vessel for about half an hour. This is the vascular phase. Also, the endothelial cells become very sticky. Now, in the platelet phase, platelets attach to the sticky endothelium and expose collagen. More platelets arrive and stick to each other, forming a platelet plug. Sometimes, this may be enough to close a small break. If not, then the coagulation phase, also called the blood clotting, begins. A chemical cascade of reactions that leads to fibrinogen being converted to fibrin, and a fibrin mesh will grow. This traps cells and more platelets, forming a blood clot. So this clotting process requires clotting factors. It also requires calcium ions, vitamin K, and 11 different plasma proteins. Proteins are converted from inactive proenzymes to active enzymes involved in reactions. This creates a cascade event, meaning that the product of the first reaction is the enzyme that activates the second reaction, so on and so forth, like dominoes falling down. For example, the extrinsic pathway of blood clotting, shown on the left, begins when damaged tissue releases tissue factor. This combines with calcium and other clotting proteins and leads to formation of an enzyme that can activate factor X. Whereas the intrinsic pathway shown on the right begins with activation of proenzymes exposed to collagen fibers at injury site. And the cascade proceeds with help from platelet factor, which is released from aggregated platelets. Several reactions occur, forming an enzyme that can activate factor X. So both the extrinsic and the intrinsic pathways activate factor X, which then forms the enzyme prothrombinase, which converts prothrombin into thrombin. This converts fibrinogen into fibrin and stimulates tissue factor and platelet factors. So this positive feedback loop rapidly prevents blood loss. Once the fibrin network has appeared, platelets and red blood cells stick the fibrin strands, and the platelets contract and pull the torn edges towards each other, and the wound closes, as the entire clot begins to undergo clot retraction. This process reduces the size of the damaged area. It makes it easier for the fibroblasts, smooth muscle cells, and the endothelial cells in the area to make the necessary repairs. At the same time, fibrinolysis begins with activation of plasma proteins plasminogen, and this produces the enzyme plasmin, which begins digesting the fibrin strands and breaking down the clot. And that concludes the lecture on Chapter 11, the blood.